Okay, so again, we have this system. Now, this is a continuation from before. And we have the parameters H1, H2, R1, R2, L. We want to know the tensions in these two cables, and we want to solve for the equilibrium. Okay, to get equilibrium, it's going to turn out to be impossible with just these forces, and that's one of the points of this exercise. Okay, so sum of the forces has to be 0. Okay, well, just look at the tension T1. Okay, it's equal to negative T1 times the cosine theta 1 times the I vector, where theta 1 is this angle here. Now that angle isn't given. That angle is determined by R1 and H1, just as theta 2 here is determined by R2, actually L minus R2, which is this side, and H2. So this side is L minus R2, and I'm going to use the blue, at least here in the picture, to indicate things that can be calculated from the quantities in white, which are the basic parameters of the system. Okay, so T1 now, as we said, is going to be negative T1 times the cosine of theta 1 and T2 times the sine of theta 1. Theta 1 is the arctangent of H1 over R1. Theta 2 is the arctangent of H2 over L minus R2. That's L minus R2 in the denominator. We could use this and this, and then take the cosine of the angle. But it's really easier just to look at the triangle and see that the cosine of this angle is this side over the hypotenuse, and the hypotenuse is just obtained from the two legs by the Pythagorean theorem. So the cosine of theta 1 then is this side, R1, divided by the length of this side, which is the square root of R1 squared plus H1 squared. And the sine of theta 1 is just H1 over that, the opposite side over the hypotenuse, same hypotenuse. So that the T1 vector is negative T1 R1 over the hypotenuse times the I vector plus T1H, T1 times H over the same hypotenuse. You can hardly read that, I can't read it, but it says the same thing this does, or this, or this. Okay, similarly, we can get the sine and cosine of theta 2, which of course is just, cosine is L minus R2 over the hypotenuse. The hypotenuse is the square of L minus R2 plus the square of H2. And I had this written before and I had it written wrong. So what I've got here, and it should be visible or legible, is L minus R2. L minus R2 over the hypotenuse. Now, you can't read this denominator very well, but it's L minus R2 quantity squared plus H2 squared. Okay, so let me write that in. And this hypotenuse is the square root of R1 squared plus H1 squared. That's what we have here. So every denominator here on any of the components of T2 is going to be this. So you might not be able to read it, but that's what it is. Okay, well, it follows then that the sum of all the forces is it's going to be T2 plus T1, the T2 vector plus the T1 vector. The T2 vector has an I component of T2 over the hypotenuse, and I left off the R2, L minus R2. And the I component of T1, you see right here, is just T1R1 over that hypotenuse, and that should be R1 squared plus H1 squared, not R2 squared, plus H1 2 squared. Okay? Careless with my subscripts. Now there's a 1 on that H. It's a little hard to see. Okay, and then we do the same with the J components. The J component here is T1H over this hypotenuse, and that's what we have here. And the J component of this vector is a T2H2 over the same hypotenuse. So those are the J components of our tensions. We also have the mg, a negative mg times J for the weight force exerted by gravity. Now gravity doesn't exert any force in the x direction, so that term doesn't appear here. Okay, well then all this adds up to 0. And if a vector is 0, then both of its components have to be 0. So the I component has to be 0, so we set this I component equal to 0. The J component also has to be 0, so this will be set equal to 0. So we can solve for T1 and T2. It's the only two variables we have, or the only two unknown quantities we have. And that's going to be great. However, that solution will not generally exhibit rotational equilibrium. And we didn't get to the rotational equilibrium on this one. That's kind of interesting. Okay, well, that's how you would set up at least the forces on this. And then you can think about how you would set up the torques. I'll actually go ahead and say just a little bit about that. The torque of the tension 1 is just the y component of T1 times R1. Because if you're going to let the moment arm run from here to here, then you have to take the component of this tension that's perpendicular to that moment arm. Now there are other ways to look at it, but that's how we can do it, okay? And over here, your torque is T2y times L minus R2. And of course you have the torque of the weight, which is going to be mg times L over 2, same that would be over here. If you solve this in general, it's not going to give you rotational equilibrium. So there's a discrepancy. And you can solve it if you wish, but what really happens is, unless you've got another force, you're not going to get rotational equilibrium. Or if you've got rotational equilibrium, then this condition is not going to be compatible with the solution down here. So that's a conundrum that we can resolve at some other point. The fact is, if you suspend the beam with this geometry, just arbitrarily, you can't arbitrarily choose these angles and these positions in such a way that you won't have, that you can both support the weight and prevent the system from correcting itself by going a little bit this way or a little bit this way. You have too many conditions, it's not going to work out.